Okay, cool. So we are on section 13 of LNL's classical mechanics titled The Reduced Mass. And Landau states that a complete general solution can be obtained for an extremely important problem, that of the motion of a system consisting of two interacting particles, in essence, the two-body problem. As a first step toward the solution of this problem, we shall show how it can be considerably simplified by separating the motion of the system into the motion of the center of mass and that of the particles relative to the center of mass. The potential energy of the interaction of the two particles depends only on the distance between them. So, as a visual, my first particle will be here, second particle is somewhere here, and they are both a certain distance from my origin. Call this R1 and R2. Now, the distance between them can just be R1 minus R2, which I will define as my new radial vector. The Lagrangian for such a system would be L equals 1/2 m1 r dot 1 squared plus 1/2 m2 r dot 2 squared minus u. And from our center of mass condition, we know that m1 r1 must be equal to the inverse of m2 r2, so they can be homogeneous. From this equation, I can now solve for R2, which would be equal to m1 r1 over m2. And plugging this into my new radial vector condition, r would be defined as r1 minus a negative m1 r1 over m2. And to simplify this, I will multiply my r1 by m2. Which will let me combine it all into one equation. R1 times m1 plus m2 over m2, which will be my new radial vector r. From there, I can simply just solve for r1 and r2. So r1 would be equal to m2r over m1 plus m2. Similarly, my r2 will be equal to minus m1r over m1 plus m2. Taking the derivatives, I would get just, well, taking the derivatives and squaring them, m2 squared over m1 plus m2 squared and m1 squared over m1 plus m2 squared. Plugging this into my Lagrangian, I would get L equals 1/2 m1 times m1 squared over m1 plus m2 squared plus 1/2 m2 times m1 squared over m1 plus m2 squared. And I can now combine these two equations into one, which would give me 1/2 m1 m2 times m1 plus m2, all divided by my denominator, m1 plus m2 squared. And we have some nice cancellation going on here. So we now get our new Lagrangian, which would just be 1/2. I'm going to label it as capital M as my reduced mass, and which would just be M equals M1 M2 over M1 plus M2, which would give me my new Lagrangian. And this is what we call the reduced mass.